Okay, that should be good now. Okay, so welcome to the second lecture on the Weil conjectures. So as we mentioned last time, the goal of these lectures is to introduce those who have not necessarily had a course in algebraic geometry to the world of Weil conjectures. And now, of course, if you have had a course in algebraic geometry, that would help, but it's not a requirement. And I'm grateful to some of the experts that are showing up and giving comments and correcting, etc. And so the goal is to present the material in a way that you, as far as possible, that you could sort of, do it on a walk around the campus. That's sort of one of the goals. And the other goal is to give, the younger people an orientation. If you want to study the subject further, you have this sort of larger overview of one of the most important results to guide you through the process. Can everybody hear me? Brechel, everybody can hear me okay? Okay, maybe then. Okay, so let me remind by something we discussed last time. So I'll try to make the lectures also as much as possible independent. So if you didn't see this last time, it's okay. But we did talk about what's called the Rosetta Stone of mathematics. So let's review this, because it's a really beautiful concept, and it's one that's very important for people who want to learn more this subject. So I will only consider 2 columns of the Rosetta Stone. It has like usually 3 columns, the third column being Riemann surfaces, but I will right now just concentrate on 2 columns. So on one side, we have number fields, which are finite extensions of a Q. So as an example, you can think Q itself. And on the other side, we have function fields, by which I mean a field of rational functions on a curve over a finite field. So in this case, as an example, you can think the rational functions fq t. Okay, and then inside here we have the ring of integers. These 2 fields that I've mentioned, these are global fields of dimension 1. That's sort of essentially a characterization. And inside them, we have a field of ring of integers, which I denote by rho. And in the examples, in the running examples, the ring of integers is just z. And on this side, it's just a polynomial ring. And inside here, we have maximal ideals, which are essentially the same as prime ideals, except the 0. So, and these are in bijection with prime numbers. And on this side, we also have maximal ideals, and they're in bijection with irreducible polynomials. Okay. And then we have the set of all ideals. Well, let me consider non-zero ideals. I don't want to, well, it's not that important. And then the ideals in Z are just parameterized by positive integers, and ideals in the polynomial ring are just, they're all principal ideals, so generated by one element. So this is in bijection with all polynomials. And then we have the zeta function attached to these, each of these settings, and the definitions are identical. So you look at the all the ideals non-zero, and you take the norm of the ideal to the power s. So this is zeta of s, where s is a complex parameter, and the norm of the ideal we discussed is the size of the residue field. And in the running example, we just get the Riemann zeta function. On the other side, if we look at exactly the same definition, then we get what's called a Dedekind zeta function of this function field. And we did an example, namely in this running example that we have with rational functions in one variable, then we got an expression for this. So, and the expression we got was 1 over, well, okay, so by definition, this is the sum f inside fqt. Let me bring this down here. 1 over degree of f to the s. Okay, and I will tell you what the expression we got for it was. Any questions so far? Okay, if you have any questions or comments and you don't feel like saying them, you can also put them in the chat. All right, so now we have the Riemann packages, so to speak, for on either side. So the Riemann package here is what we define it to be is that, okay, so there's analytic continuation of the zeta function, and that there's a functional equation. So let me write it. Analytic continuation, functional equation, and the Riemann hypothesis. And the analog of the Riemann package on the function field side would be the Weil conjecture for algebraic curves. Okay. Now, just it's important to keep in mind that, you know, in our running example, so the Weil conjecture says, as we talked about last time, we'll talk about more today, that the the zeta function on the right hand side, that this is a rational function with a functional equation, and the roots of the polynomials that appear in this rational function have all square root of have absolute value q to the 1/2, where q is our ground field. So in our running example, though, this is pretty clear, because in this example, we computed it last time, that this is just 1 over 1 minus q 1 minus s. So it's, you see in these examples that we're running, you see how much easier the right-hand side is compared to left-hand side. So the Riemann zeta function is a very complicated meromorphic function. I mean, you could ask, what is the meromorphic expansion and of the Riemann zeta function around this pole? And I don't think actually we know. I mean, like, we know that it's simple pole. Maybe we know the next coefficient, but I don't know if we know the higher ones. I have to think about it. Anyway, it's not clear to me. It's a mysterious function, but yeah, on the right-hand side, the analog of integers being the rational functions, then this is very clear. And in this case, actually, the Weil conjectures are very easy. But when you go to other fields, like the other function fields, so rational functions on curves besides A1 or P1, then higher genus curves. So in higher genus, things are a lot more interesting. And already the Weil conjectures for curves took many years to develop. So what I want to talk about today is, so we stated the Weil conjecture for curves last time, and today I want to state the Weil conjectures for higher dimensional varieties. So today, Weil conjectures for general varieties. And if you don't know what varieties are, it's not important. We'll talk about it. Okay, but before moving on, let me also mention that there's a higher analog of on the left-hand side as well. So, so here we also have higher dimensional analogs. So, namely, let me just say it in words. You start, well, okay, I can write a little bit. You start with a variety over. Very good question, Graham. Do you consider p-adics? I will in a minute. Thank you. So let me just mention that. So one can start with a variety over a global field K like Q and associate to it what's called the Hasse-Weil zeta function. If this variety is K itself, then we get back the Dedekind zeta function. And if it's K equals to Q, then we get back the Riemann zeta function. And then there are conjectures also about the Hasse-Weil zeta function, the Riemann package. But it's important to know, I mean, it becomes extremely hard. So if you're right, so then we have a Riemann package. So we have a Riemann package. So in the case of a variety of dimension 0, that's just the Dedekind zeta function. But what about variety of dimension 1? Just a curve over K. Well, if your curve has genus 1, in other words, an elliptic curve, the analytic continuation can only be proved using the Taniyama-Shimura conjecture proved by Weil. So that it was not proved. So already in the simplest example beyond what considered by Dedekind, namely a sort of a curve. Okay, we can consider a curve of genus 0, maybe that's too easy. But curve of genus 1, then has genus 1. So then this is, so then functional equation, oh, sorry, analytic continuation. I don't even know if functional, well, analytic continuation follows from was proved by Weil as a consequence of his proof of the modularity. So the only way you can prove analytic continuation is via modularity. And if you, well, that's the only known way. And if you were at Frank Caligari's lecture, Mahler's lectures, where he talked about the number 3 and Langmuir's program, so those guys proved the genus 2 case has analytic continuation. That was their major result, okay? So, and that's all we know. Genus 1, genus 2, and anything else we don't know. Even analytic continuation we don't know, let alone functional equation or the analog of the Riemann hypothesis. But the situation for the Weil conjecture, which we're going to discuss today, is much better, of course, because they have all been proved. So perhaps I should say explicitly, have all been proved. So we'll talk a bit more about them later. Okay. Any questions about this? Now, so now Graham asked about p-adic fields. So p-adics are completions of Q. So if you put, for instance, QP here, then the analog over here should be FQ bracket T. Maybe I write this as in green because this is an example. In general, you have local fields of what's called mixed characteristic and local field of equal characteristics. And these are the analog of each other inside this Rosetta Stone. Okay, so one question I want to discuss is, two questions I want to discuss. One is there a direct way we can relate the two columns? Because that would be really powerful, right? If you could, so maybe one comment first is that what makes the right-hand side easier is the existence of geometry. So there is a geometry controlling the right-hand side, and the geometry controlling the left-hand side is a mystery. So we don't know what is the geometry controlling the Riemann zeta function. Okay. So it would be very powerful if there were some sort of bridges between these two worlds, because then we could use our geometric intuition on the right-hand side to derive information from on the left-hand side, which is the really hard part. Okay. All right. Now, as far as I know, there is no global bridge. But there is a couple of local bridges. So one local bridge. So there's two local bridges, and they go by two names. So one is called perfectoid spaces. So perfectoid spaces are exactly spaces which sit at crossroads of these two. So for which, if you prove one result, I'm simplifying, but okay, if you could prove one result on one side, then you could prove it on the other side. That's sort of, and this is what Schulze got a field medal award for developing the right kind of theory, the right kind of definition of space that can, talk to both sides of this column. Okay, so that was Schulze's main achievement. Angus can correct me if I'm wrong. And there's another bridge that came earlier actually, and that's called motivic integration. So again, that's a bridge between QP and FQ bracket T, and this was first. Well, Kontsevich, there's an interesting story about this. So Kontsevich was on a train going to give talk in Paris about something else, and apparently on the train he just decided to, think about this problem, and so he ended up giving a talk which was different than his abstract about motivic integration, which started a whole industry of people. So this is two different bridges between these two sides of the Rosetta Stone that have been extremely powerful for proving results. Okay. So, maybe I'll show you a picture of Peter Schulze. Here's Peter with another one of our favorite mathematicians, Jordy Williamson. So I have I have a nice story of meeting Peter. So I was in Chicago at the time. I'd finished my PhD, had left for postdoc, and came back to give a talk. I'd proven some conjectures of dream field, and I thought, oh, that's so cool, So then I was in the same office as Peter Schulze. This picture is from 2016. This was 7 years earlier. So he was literally like a little kid, and he was like 20 years old maybe, with long hair, and we were in office mate. I was like kind of confused what this kid doing as a visitor. And anyway, so he's like, what are you working on? And so I started explaining, and within 5 minutes I was done, because he completely understood what I was talking about, and there was no mystery whatsoever. So then I asked him, what are you working on? Then he proceeded to talk for like 10 minutes, of which I understood nothing. But anyway, at the end, he said, oh, there's some interest in our group on the stuff you're working on. Why don't you write to my supervisor, who was Rappaport? Maybe you can come to Bonn. And that's how I ended up in Bonn, and that's how I met Jordy nearly 11 years ago. Okay, so that's a bit of personal history for you. All right, so let me go back to this page. Any, where was I? Yeah, any questions about any of these? Sorry. All right. So Alan asked, well, what about applications of the Weil conjectures? Okay. So I was going to talk about that later, but maybe we should talk about it now. There's many applications. I just say a few applications. So I know not in a historical order. So applications of Weil conjectures. Not in any particular order, but just some of the ones that I like and I'm familiar with. So one is to mirror symmetry. So there is this beautiful theorem of Batyriev from around 95 that says that let X and Y be Calabi-Yau varieties. So variety, you can replace it by Calabi-Yau manifold, but varieties are actually allowed to be singular, and that case is interesting here. So then if X and Y are birationally equivalent, so what that means is that they're they can be, they're equivalent if you use not holomorphic maps, but meromorphic maps, so to speak. So your maps are allowed to have poles that find in many places, but then they have inverses. So then they have the same Betti number. Okay, we are getting a bit ahead of ourselves in application. So there are words that you might not understand, but you know, it's just good to put some applications down. And the way Batyriev proved this was using the Weil conjecture. And this was one of the sort of major mathematical manifestations of mirror symmetry, which actually this was the exact theorem that led Kontsevich to his theory of motivic integration, because he wanted to give a proof of this theorem that didn't use the Weil conjecture. But so historically, the first proof was given by Weil conjectures, and still in many cases involving mirror symmetry, the only tool we have is the Weil conjectures for establishing relationship between cohomologies. So that's one application. Second application is sort of more generally cohomology of moduli spaces. And this is the area that my students and I are working on. So what moduli spaces do I have in mind? Example, moduli of representations of fundamental groups of surfaces, or moduli of things called Higgs bundles, etc. And it turns out that the only way to access the cohomology of these moduli spaces, many of these moduli spaces, is through Weil conjecture, by counting points over finite field. Question is the converse of one true. I don't know. Sorry. Right. So Weil conjecture gives you a novel way for computing cohomology. That's the sort of the slogan. So the third element, it was the proof of fundamental lemma by Ngo. So fundamental lemma was something that was stated first by Langlands. A bit of history for you, stated by Langlands, I think first in a talk, and then in sort of some conference or something, you know. And he thought that this is just some lemma that should be given to a grad student to work out. But then it turned out to be absolutely fundamental, as the name suggests, and that nobody could prove it. So this was a statement about, if you wish, some integrals, some p-adic integrals, so over QP. Okay. Then what happened was that so Waltzprager and independently Thomas Hales proved that the story over QP, fundamental lemma over QP is equivalent to fundamental lemma over, on the other column of the Rosetta Stone. So Thomas Hales used motivic integration for this, okay? So he proved that if you can prove it over function fields, then you have done it over the QP. And then Ngo proved this over function fields by counting points of Higgs bundles, actually, of fibers of, of certain Higgs bundles. So Ngo proved FL. So by using the Weil conjecture, because the Weil conjecture somehow, right, and people realize that this fundamental lemma comes down to a statement about cohomology of certain varieties called Hitchin fiber. And Ngo proved the statement about the cohomology, or rather a slightly weaker but sufficient statement, by counting points over phi f p and using, let me just say by using Weil conjecture. So that's another amazing application of the Weil conjectures. And the fourth one that I want to talk about is actually one of the first applications, which is due to Deligne. So there's this amazing theorem of Deligne. And in fact, it was while thinking about this that he came up with the proof of the Weil conjecture, the last one, the Riemann hypothesis. So this is a really remarkable sort of turn of events, which I don't actually understand the details and would love to. So, so Deligne showed that the Weil conjectures imply what's called the Ramanujan conjecture. And the Ramanujan conjecture, I want to spend a few minutes talking about it because it's really beautiful. And well, our lectures are supposed to be informal and have historical interludes, so we can have a bit of a bit of fun. All right, so I'm going to talk more about this this fourth one. Any questions about this page before I move on? Okay, so I want to actually read an excerpt of the interview of Timothy Gowder with Deligne. So this is Timothy Gowers, who was another field medal, was interviewing Deligne for the Abel Prize when Deligne won the Abel Prize. So, by the way, the stuff before the interview is also interesting. This is taken from Milne's note on the Weil conjectures. So we can read a little bit. Again, we're getting ahead of ourselves because Grothendieck hasn't even entered our story yet. But anyway, let's read together because it's interesting. Grothendieck attempted to deduce the Riemann hypothesis in arbitrary dimensions. So by that, he means the Weil conjectures in arbitrary dimensions from the curve case. But no devisage works for him. So devisage is a method of reducing things from higher dimensions to the curve case. So that's, but the footnotes are actually interesting as well. So you read the first footnote. Serre writes, he was not the only one. So did Weil around 1965. He looked at surfaces, made some computations, and tried vainly to prove positivity. He talked to me about it, but he did not publish anything. So Weil also tried to prove his conjectures by sort of reducing to the curve case, but couldn't do it. And by the way, Serre, I was reading about Serre. So Serre got a Fields Medal in 1954 for his work on topology. So developing what's called now the Leray-Serre spectral sequence and computing some homotopy groups of sphere which is the holy grail in algebraic topology. But once he heard about the Weil conjectures, he sort of, so by the way, and he was the first person apparently who was not an analyst who won the Fields Medal. So this was all in series. Yeah, and what he won the Fields Medal for was all, yeah. So he won it at a very young age. But so once he learned about the Weil conjectures, he sort of slowly switched fields and sort of moved towards the algebraic geometry. So he was actually the first of many who. So then, when you look at the distribution of Fields Medals, now it's become much more heavily towards arithmetic geometry. Some people say too heavily, as opposed to say analysis. But so that was the decisive step, sort of started from Serre. And once he got interested in Weil conjectures, then he got Grothendieck interested. And so here's Serre's comment about Grothendieck. So Grothendieck hoped to prove the Weil conjectures by showing that every variety is birationally a quotient of a product of curves. But Serre constructed a counterexample. See Grothendieck-Serre correspondence. And I have actually this copy of Grothendieck-Serre correspondence, which is a book published by AMS and has all of their letters. And sort of incredible how they did math. So, I mean, it's very different to how most people do math. So basically, Grothendieck never read any references. So he just tried to create everything from, zero principle. And he would write it in letter to Serre, and Serre was very good with references and extremely sort of ingenious coming up with examples. Like he would come up with counter examples or be like, oh, that person has already done these, or like, I think we can do this better this way, and he'll send another letter or another question and sort of go back and forth between them. And that's how sort of the modern algebraic geometry was born, on the letters between these two. But okay, so let's now, continue reading. After Grothendieck announced the standard conjectures, so maybe we get to that at some point in this series, the conventional wisdom became that to prove the Weil conjectures in higher dimensions, one should prove the standard conjectures. However, Deligne recognized the intractability of the standard conjectures and looked for other approaches. In 1973, he started the mathematical world by announcing a proof. Okay. Now, Tim Gowers asked, given the clearly absolutely remarkable nature of your proof, it does make one curious to know what gave you the idea that you had a chance of proving it at all. So Deligne says, that's a nice story, in part because of Serre, and also from listening to lectures of Gudemont, I had some interest in automorphic form. Serre understood that the p to the power 11 divided by half in the Ramanujan conjecture should have a relationship with the Weil conjecture itself. I understood the connection between the two, and later on he says that in fact he got motivations from key parts for proving the Weil conjectures from the theory of automorphic forms that was being developed by Langlands and Gudemont and others. So, but what I want to focus on right now is just for a moment, what is this Ramanujan conjecture, and what is this p to the 11 over 2? So let me write about Ramanujan conjecture. So to talk about that, we need to define the Ramanujan's Taos function. And this is another one of my absolute favorite definitions in mathematics. So this is a function tau, which goes from n to z, and it's defined as follows. It's defined by an equality. So the equality is as follows. The tau is the coefficient of q to the n in the following expansion. So you write the product of 1 minus q to the n to the power 24, and take the product of that over all n and multiply by q. And then you gather all the powers of q together and then keep track of the coefficient. Okay, so if you do that, you will discover, I actually haven't done it. I just copied from Wikipedia. But this is elementary, the first few coefficients. Okay. So now it's not clear why Ramanujan wrote down this definition. So Ramanujan, it's not clear how he came about to whatever it was that he did. He sort of had these divine revelations, sometimes in sleep or sometimes in when he was awake. So here's a picture of Ramanujan with a quote by him. An equation means nothing to me unless it expresses a thought of God. So, and the equations and definitions that he wrote were, completely baffling to other mathematicians. In particular, well, many of them didn't understand it and dismiss it, but the one person who did was, one of the people who did was Hardy, to whom Ramanujan wrote a letter. Well, Ramanujan was a clerk in some post office in some tiny town in South India. And he writes letter to the most prominent professor in Cambridge in mathematics with a mass of formulas, and so Hardy, sets aside the letter for a while, and then one day he starts looking at it, and he's like, it looks like it makes sense, some of it. So then he goes to Littlewood, his famous collaborator, and they just pour over this letter for weeks, and to their amazement, they discover that there's a lot of gems in there. So one of the things that was in Ramanujan's writings was this tau function, and Ramanujan conjectured that tau is a multiplicative function, so that i.e. tau AB equals tau of A times tau of B whenever GCD of A, B equals 1. And that tau, so that means that to find tau, you only need to find it on prime powers. Okay? And then on the prime powers, there's a recursive formula, namely tau to the p to the j plus 1 is tau to the p to the j plus 1 minus p to the 11. I think there's a tau missing there. Tau of p to the j minus 1. Hopefully I didn't. And then third was that the absolute value of tau is tau of p is less than or equal to 2 times p to the power 11 over half. Now, I think in modern, well, now we would say that tau is an example of a modular form. Am I right, Angus? Is tau itself a modular form? Right. And in some fashion, it was actually
sorry. That is incorrect. Sorry. The tau is the coefficient of a modular form. The function that packages tau together is the modular form.
Right. So this Q expansion is the Q expansion of a modular form.
Yeah.
And actually, the significance of the Ramanujan conjecture, the last one, which I think was the remaining one that was open, I'm not completely sure about the significance, but there was sort of a lot of people that were interested in this. Angus, do you know, or anybody, do you know what the significance of it was somehow? Yeah, so that's.
I mean, certainly the function that packages information, this modular form, sometimes called the modular discriminants or elliptic discriminants, is an important function for lots of reasons related to modular curves, elliptic curves. So understanding its properties are important. The function tau as itself, I'm not sure what people would have been interested in.
There's a good comment in the chat, which I've forgotten about. Yes, tau is related to the partition function. Right, so there's a close relationship between tau and the function that counts the number of partitions of a given integer n, which is a problem that Ramanujan was very much interested in. So Delim and Serre first, and then Delim saw this and discovered that there is a relationship between this p to the 11 over 2 that we see here, and q to the I over 2 that we see in the Weil conjecture. Well, we haven't seen it yet, but it's these are eigenvalues of these are the roots of the polynomials that appear in the rational function. And sort of that connection was actually what led to the proof of the Weil conjecture eventually. Okay. So, okay, while we're actually talking about Ramanujan, we should say hi to Hardy as well. So here is a nice quote by Hardy. The mathematician's pattern, like the painters or the poets, must be beautiful. The ideas, like the colors or the words, must fit together in a harmonious way. Beauty is the first test. There is no permanent place in the world for ugly mathematics. So I think that sort of, as we go on in these lectures and you learn more about the Weil conjectures, I hope you agree with me that this is a very beautiful area. So if something happened to our civilization and somehow knowledge was lost and was found, say, again, 2,000 years later, I think people even 2,000 years from now will enjoy the story of Weil conjectures, just as the Renaissance people enjoyed rediscovering Euclid's elements. You know, that's so that sort of beautiful piece of mathematics is eternal. That's sort of what Hardy is saying here. All right. So now what I want to talk about, right? So I want to talk about Weil conjectures in higher dimensions, but first I have to tell you a little bit more about points. What do we mean by points in algebraic geometry? I started talking about this last time, but I want to sort of remind and move on from there. Any questions so far? All right. So what I need to discuss is the notion of rational points versus closed points. Now, what we discussed last time was the notion of closed points, what we call closed points. So last time I told you that points, when we're discussing points in algebraic geometry, one way to do it is to consider maximal ideals in our range. Okay, so let's just be very explicit. Suppose you're given a plane curve. So X, a plane curve. So defined by fxy equals to 0, some polynomial. Fxy equals to 0. If you want, you can think about an elliptic curve. So like that. Okay, so example, what do we mean by a point on this curve? So last time we said that a point, so today I want to emphasize, call this actually a closed point. The closed point on X is, by definition, a maximal ideal in the ring of functions on X. So suppose this is over some field K. So in our running example, so let me write our example, So in our running example, this will be just kxy, polynomials modulo the ideal generated by f, which is just kxy modulo the ideal, y squared equals generated by y squared minus x cubed plus x, okay? And I gave some justification for why this is reasonable using what was called Gelfand duality, okay? But there's another way you can think of a point, namely, well, a point is something that satisfies that equation. That's a very natural thing to do. It's even more natural than taking perhaps the maximal ideals. So another thing that I want to define is that a K point, a K rational point, which sometimes I just abbreviate by K point, so let me just define the set of K rational points and denoted by xk. That's just the set of xy in K2 such that fxy equals to 0. I mean, well, when in high school you learn what is a curve, when you want to plot a curve, you just find x and y that satisfy that equation, right? That's it's very reasonable to call these x and y's the points on that curve. Do you mean that Delin proved Ramanujan using Weil? Yes, yes, that's what happened. Can you explain how? Okay, I think how Weil used Ramanujan conjecture. Yeah. Okay, maybe that's a good discussion for our Slack channel. By the way, there is a Slack channel, and it's as useful as you make it. So it's for the community of people that are interested in this. So and these kind of questions can definitely be discussed there. Okay, so that's a rational point, but we can also, the key thing is that K need not be algebraically closed. And in fact, we want it to be a finite field, which is not algebraically closed. So if K prime is a finite extension of K, then we can also look at K prime points. Well, which is the definition is all xy in K prime such that fxy equals to 0. And this can be radically different, right? Just imagine another example, maybe not the elliptic curve is also radically different, but the more obvious example is just consider fxy x squared plus y squared plus y has no r points, but plenty of c points, right? Because there's plenty of pairs of complex numbers satisfying this equation, but no pair of real numbers, okay? So now, how do closed points and rational points compare? So here's an exercise. Maximal ideals in our ring are in one-to-one correspondence. So these are the, by the way, AKA closed points, right? AKA closed points. They're in one-to-one correspondence with what? With K bar points, K bar rational points of X up to Galois conjugacy. Galois group of K bar over K action. So you take your points. So let's say if you were over R, you look at the C points, you have plenty of C points, but some of them lie in the same orbit. So you have, just think about it this way. You have an equation, even an easier equation, x squared plus 1 equals 0, right? So what are we saying? This x squared plus 1 equals to 0, it has two roots, right? These are the two C points. But then if you want to think of it as sort of in R, you have to sort of group it together. So you have to consider it modulo the Galois action, okay? And the idea here for this exercise is the same. And once you unpack it, actually, if you understand what each term means in the exercise, it's actually not very easy. And it's true not just for curves, but actually any system of polynomial equations that we take. So, and the reason I'm saying this is that, so let me actually write what I just said. Any questions about rational points versus closed points? So this is actually one of the really confusing things in algebraic geometry. There's many different notions of points. Whereas in topology or geometry, usual topology and geometry, you just had one kind of point. In algebraic geometry, you have many different kinds. But so let me just say then that same thing holds if we consider holds if X is defined by a system of polynomial equations. What do I mean by that? I mean, like you have L different polynomials in several variables, and X is defined to be, so X is the, in some sense, set of solutions of this polynomial. But when we say set of solutions, we have to say over what field, right? That's the point of our discussions right now. Over what field? So for any field, K, any field extension K prime of K, we can look at the set of solutions over that field extension. So this is alpha 1, alpha n, such that fi of alpha 1. So these are inside K prime to the n, such that this is equal to 0 for all I, for all the polynomials in question. Okay. So this is what we mean by rational point, K prime rational point on X. And if we are over a finite field, we can of course count the number of such rational points. So if K is equal to FQ, then set NM to be the number of solutions to the system of our polynomial equation over that finite field. Okay. Is everybody clear what we're doing here? We're taking a bunch of equations, looking at their solutions over field extensions of the ground field. And then because we're over finite field, we can count. Now,
this last X, it can be defined. This is for general L Fs, right? Not just one F?
Yes, so this is for, right, 5 many Fs. Thank you. Okay, now the relationship between the number of rational points and the number of closed points is given as follows. So lemma. Now, why do I want this relationship? Is because remember the zeta function that we define for curves is given in terms of number of closed points, number of maximal ideals. I want to rewrite that in terms of rational points because these are easier things to discuss also for higher dimensions. So the lemma is that Nm equals the sum of D divides M, D times the set of maximal ideals in our ring R. So what is the ring R? Let me write R here. R is the ring Kx1, xn modulo this ideal generated by this polynomial. So if you look at the maximal ideals in here, such that whenever you have a maximal ideal, the size of it is finite, so it's q to the d, because we're working over a finite field. So I'm assuming in this lemma that K is a finite field. For Nm to be defined, K needs to be a finite field. And the claim is that we have this relationship between Nm and the number of maximal ideals. So let me put, sorry, I should put here, this absolute value means the number. So let's call this maybe AD. So AD is, this side has to do with closed points, with maximal ideals, or in other words, closed points. This side has to do with the rational points, okay? This lemma actually is very easy once you understand what the statement is. So proof, very easy. Why? Because each maximal ideal P defines R mod P rational points, because these are exactly the solutions that are in the same Galois orbit, okay? And these points are in FQ to the M if and only if the size of R mod P is FQ to the D for some D dividing M. So R mod P has to be of the form Q to the D, where D divides M. And the number of such a things is AD, and each of them gives you so that many rational points. So you put this together and you get this formula. The details are not important. I'm not expecting you to follow the proof if you haven't seen it before. But I do expect you that to be able to actually understand this if you go back home later and go over it. Okay, it's not actually that hard. We're not doing anything complicated, so to speak. So it's a good exercise to try to, it does not require anything except like some basic things about maximal ideal. It could be given in a, abstract algebra course, undergrad abstract algebra course, okay? So we're not doing anything too complicated. But why are we doing this? I just want to remember this formula for later. I will bring it out later as well. So why are we doing this? We're doing it for the following reason. So now suppose X is a curve. And remember that I defined the zeta of X to be the sum over all maximal ideals, right? Of 1 over Ni to the S, right? This was our definition. So here, well, here, if I assume that X is an affine curve, things will be easier, because then OK would just be simply field of functions on our curve. If it's not affine, then you have to dance a little bit, but let's assume affine curve. So this is the Dedekind zeta function of this function field. So this is, in other words, the zeta function of this curve is the same thing as the zeta function of its function field, which was defined on the first page of today's talk, okay? In terms of maximal ideal. And now I want to prove the following proposition. Zeta of X actually equals the following expression, exponential of M bigger than or equal to 0, nm q to the minus ms divided by m. Now, when you first look at this, it sort of looks strange. So let me sort of, and what's, when you look at references on the zeta function, many people just define the zeta function this way. So zeta function is you count the number of solutions over finite fields, and you put it in a generating series. That's what it is, right? So let me actually write that. So zeta is the generating series for nm, which remember, nm is the number of solutions of X over the finite field fq to the m. So whatever the equations defining X is, you just look at its solutions over fq to the m. So that's the conclusion of the proposition. But many people actually define the zeta function this way. And it's a bit weird to have, you might ask, why is it that the generating series is written in such a weird way, with the exponential and divided by m? it's precisely because so that it agrees with the definition of zeta function as defined by Dedekind, which generalizes the Riemann zeta function, right? So if you wrote a different, so you could have imagined I could have written a generating series. The most natural generating series, of course, would just be simply to write nm q to the, I don't know, maybe if you want to bring s into a q to the minus ms, okay? But that would not be equal to the zeta function when you sort of, if you define the zeta function via the route that we've defined via the Dedekind, and in analogy with the Riemann zeta function, right? If you define it that way, you lose analogy with Riemann zeta function. Okay. So let me also remind that we have a product formula here. This is product over all. Sorry, there was a mistake here. This was over all ideals. And then when I take the product, this is over prime ideals or maximal ideals. Okay, so I corrected that typo. All right. Now, proof of this is actually a computation, but I want to give it, you can close your eyes for 5 minutes and rest if you don't want to see the proof. But I want to give it, there was at least one request to explain, you know, why this is true. So let me just give the proof, and it's not hard. It's just you, yeah, so recall, so proof. First, I recall that I had this integer defined in the previous page, which was the number of maximal ideals of degree D. Well, by that, degree means that R mod P is Q to the power D. So now let me so then the zeta function, I can write it like this. Zeta function is the product, D bigger than or equal to 1, of 1 minus Q to the ds to the power minus AD. So this is because in the so, okay, I skipped a step. Let me move this. First, write the definition of, or the Euler product of zeta. So that's product over P of 1 minus NP to minus S to negative 1. But remember that NP is Q to the D. So, so if I look at, and then the previous lemma said that the number of, so the number of maximal ideals of degree D is AD, and their contribution is D. So, yeah, so maybe, so do I need to say more, or is this? So Alan seems to be happy. Chris, are you also happy? Because Chris asked me about this question. Okay. So if you're unhappy, ask Alan or Chris. Okay. And I'm going to just make a change of variables. I'm going to write this as 1 minus, because 1 minus t to the s to the power minus AD, where t, remember, t is my variable for q to the minus f. So I make a change of variable here to write it like this. And now I'm going to take log. So therefore, log of zeta of x. Well, what happens when you take a log? You just, you know, well, we just follow our nose now. So this is log of 1 minus, sorry, I think I made a, this should have been t to the d, because I absorbed the s into t. So what remains, I absorb the minus s into t. So what remains is the d. So then I get log of 1 minus t to the d to 1a over d, which is, so, okay, so this proof is a computation, which probably cannot be done on a walk around the campus, and that's why you're allowed to go to sleep if you want. But okay, if you're awake, we continue. So we're just expanding, let me just write this as minus log of 1 minus t to the d, and bring the AD down, so that's what it looks like. And now we're going to use the fact that minus log of 1 minus x has a Taylor expansion given by x plus x squared over 2 plus blah, blah, blah. And so that gives us that this is sum t bigger than or equal to 1 of AD sum e bigger than or equal to 1 t to the dE divided by E. So that's the Taylor expansion of this pink thing. The Taylor expansion becomes this. Okay. And now we put this together, we get the sum of m bigger than or equal to 1, sum d divides m, d AD, t to the m. So this is just some rearranging of this sum. And this now, by the previous lemma, this what I'm painting in yellow, that's just nm. So this is equal to the sum of nm t to the m divided by n. Okay. So in particular, so this is just some computation, which I've written, and you can go home and check if you're satisfied with it. But in particular, Chris had asked me how to account for this denominator m that we're putting in this Q expansion, okay? And the answer, when you go through the computation, is that the denominator, there's two contributions to the denominator. One contribution coming from the expansion of log, so from the Taylor expansion of log, and the other one is coming from the Galois orbits. So they're both contributing to this denominator m. Okay, so if you meditate on this computation, you will see the contribution of both of them. Okay. All right. Any questions? Typos, mistakes? All right. So now you can come back from sleep. So all I want you to remember is that this zeta of x equals this exponential for curves, right? But now that we have it for curves, we can define it for all varieties with exactly the same definition. So by variety, I mean solutions to a system of equations. Let's say for now, that's what we mean, an affine variety. So, but it's easy to generalize it. Given a variety x over f cubed, we define this zeta of x to be the exponential and nm over m t to the n. Okay, and if you want to write it in terms of, well, if you want to write it in terms of q, then you have to replace t by q to the minus mn, or q to the minus s. And the proof that we just gave also tells you that this is a product over all prime maximal ideals in our ring, or equivalently over all closed points. So closed points, which is the same as maximal ideal in the field of functions on x. Okay. So, in other words, we defined, so let me recap. We defined the zeta function for curves in analogy with the Riemann zeta function as a sum over 1 over the norm of ideals in the ring of functions on that curve. This sum has a product formula, product expansion in terms of maximal ideals on that curve, just like Riemann zeta function has a product expansion in terms of primes. Now, that sum does not generalize to something reasonable for higher dimensional variety. To generalize to something reasonable, instead of taking maximal ideals, we have to look at rational points. Okay, and then we get an expression like this. We can rewrite our sum for a curve in terms of an expression like this, which then generalizes to an arbitrary variety. On the other hand, the product formula that we had, so the product, that one a priori makes sense for any variety. So if you take the maximal ideals, you always get the right thing. Okay, so that's always the right thing. But if instead of this definition of zeta, you took the definition with all ideals, that would not be the right thing in higher dimensions. Okay, so that's the recap of our journey so far. And motivating, I could have started this course by just this definition. Define the zeta function to be exponential of nm divided by m to the t to the m. But then it would be completely mysterious as to what this has to do with the Riemann zeta function. But now we've sort of built a solid sort of table of analogies and a solid bridge between the Riemann zeta function and this function. Okay? Any questions? Joe Bain, T to the D. Did I miss the T to the D somewhere?
Oh, that was from a while ago. Don't worry.
Okay, find the missing T to the D. M is any positive integer, yes. And probably I mean D points rather than R mod P points. Yes, R mod P is the norm of P. Thank you, sorry about that misspeaking. Okay, so now that we have our zeta function in a motivated way, let's state the Weil conjectures. So, the Weil conjectures, which is the Riemann zeta, with the Riemann package for this zeta function. So first of all, zeta of x is a rational function of the following form. So these are polynomials. And for historical reason, we name them like these, P1 to P2. Well, maybe not just for historical reason, but that's the right. So these are polynomials. Remember the example that we had of just the affine line, zeta function of the affine line, that was 1 over 1 minus, I think, qt, right? And if you had a projective line, you had a 1 over 1 minus t multiplied by that. And more generally, P2 is always 1 over 1 minus t, and the last guy is always 1 over 1 minus qt. And q is a prime power, so it's like 5 or 25 or something like that. So this is the analog of analytic continuation, which is much stronger here because you actually have a rational function. So then we have the functional equation, which says that if you take q to the d t, this is plus or minus q to some q to some power, and then t to some other power. Chi is the Euler characteristic, but let me just write it for now. And then zeta x of t. So the functional equation is when you plug in 1 over t over q to the d instead of t itself, then you get a functional equation like this. And finally, we have the Riemann hypothesis, which is if you write pi as these, look at the roots of these polynomials, then the roots of pi all have absolute value q to the I over 2. Okay, so if you look at our version of Weil conjectures for curves, you see that it easily reduces to that case. So maybe before moving on, the first Weil conjecture was proved actually by Dwork in a surprise for the mathematical community. So this was 1960, for which he got a field medal. This one was proved by Grothendieck with significant contributions by Artin. This is 1960s, for which he got a field medal. And this was proved by Deligne in 1970s, for which he got a field medal. So, and not next week, but the week after, Angus is going to tell us about Dwork's proof of the Weil conjecture, of the first Weil conjecture. Any questions about the statement of the conjecture? What is BI? Excellent question. Is X proper? Oh yes, sorry, I should have said that. Otherwise, the functional equation. I mean, everything else works for not X proper, but for functional equation, yeah. I mean, okay. So, and then the numbering may not work. So let's assume X is complete. So remember, we were talking about Riemann package is better stated when you complete the zeta function, right? The same thing holds for the Weil conjectures. You can state them for any variety, but actually it's best stated when you complete the variety. So thank you very much. That was a definite X complete. If you wish, projective. It's embedded inside a projective space. Okay. Thank you very much, Alan. And I'll get to Graham's question in a minute. Any other questions or comments?
So do we require X smooth for 2 to hold?
Do we require X smooth? Do I need also smooth? Probably, yes. Sorry. Yes, because in the curve case, it would already fail, I think, if it's not smooth. Yes, complete and smooth. So think a projective manifold. Okay, so a manifold that you can embed inside, algebraic manifold that you can embed inside, like projective space, but then cut out by some homogeneous polynomials where there's no singularity. Okay, I think that's a, yeah. Any other assumptions that I'm missing?
There are analogs of this conjecture in the non-smooth case, but it's, I don't know, maybe less beautiful depending on your perspective. Certain things have to be modified. The weights can be mixed, is one way to say it. These
right.
The statement about the absolute values has to be modified.
Yes. And in fact, so Deligne discovered these analogs for the non-singular one, and that discovery, which is called his second paper on the Weil conjectures, turned out to have a lot more application. So almost, I think most of the applications of Weil conjectures comes from Deligne's second paper, not the first paper. So it's yeah, and that's the sort of yoga of weights that comes. So that was Deligne's. Okay, so maybe I can say just a word about. So that was Deligne's sort of way of bringing Hodge theory to characteristic P. So that's, in this Rosetta Stone, there was a third column with Riemann surfaces, and you have Hodge theory there. And Deligne sort of not only brought Hodge theory to the finite characteristic, but also generalized Hodge theory to non-singular settings as a result of that translation. So that's another application of Rosetta Stone, by the way, is a generalization of Hodge theory to to singular objects. Right.
Maybe it's Masood, that like in that circumstance, there's a really sort of more basic consequence, which is really useful to know, which is like this whole picture just gives extra stuff for free on the cohomology of singular algebraic varieties. Like it gives you extra linear algebra floating around. And so even if you don't understand any of the proofs of any of this stuff, like you can still just say, great, I have extra structure. It just makes my life easier. Like you've sort of got not quite an extra grading, but nearly an extra grading on the cohomology of potentially singular.
Yeah, I mean, I would say there's probably hundreds of mathematicians, if not thousands, that use Weil conjectures one way or another. But the number of people actually understand the proof is, it's probably in tens, right? It's so yes, you just look at it in as a black box. But we will demystify some parts of it anyway. Okay, so let me end by answering what is this BI, because that's actually this exact question that Graham asked. What is the degree of these polynomials that occurs? This is the exact thing that electrified sort of the mathematical community when they first saw these conjectures, because what Weil said was that suppose, so Weil said that if, suppose your x is given by polynomials that are defined just over integers, right? So suppose you have some polynomials over integers, like, with integer coefficients, and suppose you reduce this modulo p to then count points, right? Then these BIs that you're seeing is exactly the dimensions of the cohomology group of X, but the C points of X. So the C points of X are then a complex manifold, because we're assuming non-singular. And these BIs are known as the Betti numbers. So what Weil explained was that these BIs that we're seeing coming up in the Weil conjectures are actually the Betti numbers of the associated manifold. So to any system of equations, you can associate the corresponding manifold. Suppose it's non-singular, there's no singularity. So corresponding manifold over C. And so what they basically, so first of all, this was the first indication that, Betti numbers are algebraic and can be defined over characteristic P, which was a big surprise. So in other words, one can compute BI by counting points over finite fields. So this was a big surprise. And another thing that Weil explained that maybe we will talk about later is that if you could find a cohomology theory for objects over characteristic P, which behaved like cohomology theory of complex varieties, then you could prove at least the first two Weil conjectures, not the Riemann hypothesis, but the first two. Would be the right explanation for the rationality and the functional equations. And in one of the future lectures, I will explain why the right cohomology theory would explain the first two Weil conjectures. So let me also say, Weil also said that the right cohomology theory, when I say right cohomology theory, I mean, he gave some list of properties also. They're now known as Weil cohomologies. the right cohomology theory will explain, well, let me say, the existence of the, just to emphasize, the existence of the right cohomology theory will explain the first two conjectures. So part 1 and 2 conjecture of the Weil conjecture, okay? And then the race was on to find this cohomology theory. And that's essentially what Grothendieck and Serre and Artin, etc., were able to do with L-adic cohomology theory. So, okay, I think this is probably a good place to start. So it did get a bit technical in the middle, this lecture, but next lecture actually is going to be a bit of a break, because next one, we're just going to talk about Riemann zeta function, the original Riemann zeta function, and we're going to take a walk with Riemann zeta function and see how much we can understand about it in a conceptual way, okay? So, so that will be the next lecture, and then the lecture after, Angus will tell us a little bit about how Dwork went about proving the first of the Weil conjectures, and this has to do with what's called p-adic analysis. So you do analysis, but instead of over reals, over p-adic fields. Okay. Any questions or comments?
Could you maybe just repeat what you've just said? So, like, just clarify things. So, so first observation of Weil is that Bi is the dimension of the cohomology for the C points. And then over a finite field, there's no manifold anymore, but you can still compute, right?
There is no manifold. So what does cohomology even mean, right? So that was the big open question, right? So, I mean, that's, you have, you know, if you look at just points, you have finely many points. What can you do with finely many points, right? How can you build geometry from finely many points? That's somehow, that's essentially what, you know, Grothendieck and his school build.
Great, thanks.
Welcome. Other questions?
Masood, I asked this in the chat earlier. I was just wondering,
sorry.
That's all right. Is there an analog of the special values of Dedekind zeta functions for these functions of algebraic curves?
Functions of, you mean, is there analog of special values in the function field?
Yeah, as in, like, you know, if I evaluate this at, say, even integers or odd integers, do I get like the volumes of certain moduli spaces?
Good question. Good question, Joe. I mean, I would say, like, you know, there's these conjectures by Bailinson about special values of L functions, of Hasse-Weil. So, but those are usually for number fields, and you can ask, is there analog of that over function field? So you're translating to the, you know, across the Rosetta Stone, across the column, and you can ask, what do they mean, and have they been proven? You have to look at papers of Bloch and Bailinson and these guys. I'm sure people have written something about it, but I just wouldn't know. Yeah.
Okay, sure. Thank you.
I mean, one thing which you can say is that, like, the class number, like, there's a class number formula for the zeta function, and in the sort of finite field case, it's much easier to say what the class number is, because you've got a correspondence between, like, ideals and sets of points, right? And, like, sets of points are basically what you're counting in the zeta function. So, like, once you can work out what this equivalence relation is, quotient that out, you'll get a class number. And so there is a way to extract pick from as, like, a special value of zeta function, I believe. But I can try and track down the reference for you, because I don't really remember it. But morally, it's sort of.
Cheers. Yeah, thanks.
Yeah,
Chris.
I mean, that appears in the functional equation for the Dedekind zeta function. That's called the analytic class number formula, right? And I think what you're saying is that the analytic class number formula is more transparent in the function field case. It would be good to actually learn more about that. But for me, I mean, but it's yeah, it's not surprising that things are more transparent in the function field case because there is geometry around, as you said. All right. Other questions or comments? All right. Well, we'll see you guys and ladies next week for the some fun with Riemann zeta function.
Thanks.
Bye-bye. Thank you, everyone.
Thank you, Mr.